Recording started.
Okay, so hello, welcome to this week's graphics programming meetup. We're looking at the too early Z or not too early Z article uh, by the real MJP. So let's look into it. Yeah, I do take for granted early Z testing. Z prepasses exist. And forward rendering is still viable because of it, somewhat. Yeah, Z prepass and early Z is like baked into the hardware old, so it's not a new thing. I Yes, this is why I'm reading the article. Mhm. It's the overview of what early Z is, how it works, when it doesn't work. Nice table. Okay, there's a tester app that is what what found these findings, or rather what confirmed these findings. Um, that's nice. So if we wanted to dive into what the numbers look like, we could use this handy dandy test app, which has a nice overlapping triangle, a bunch of different modes and settings. Okay. Yep, this is going to be a desktop article, not mobile. So no assumptions about mobile hardware can be drawn from this. Okay. The logical rendering pipeline. It's abstract, not really tied to hardware. It's more of a description of what should be happening and not exactly what's happening. Yeah, its abstractness. It allows for performant hardware. Yep, the D3D pipeline got input assembly, programmable vertex stage, programmable hole shader, a tessellator, hardware stage, programmable domain shader. I guess the round edges are programmable and the square ones are fixed function. The domain shader geometry, optional stream output, which is a readback mechanism. Um, rasterizer, pixel shading, and then the output merger. I'm used to for Vulkan terminology, but like even in my naivety of not being a D3D12 person, I can tell you exactly what these revert to in the OpenGL and Vulkan terminology. Just yeah. So yeah, basically all depth operations are ostensibly going to happen in the very last stage, the output merger. Um, yeah, if you're familiar with modern hardware, seeing the description of output merger being at the very end is kind of odd, but in a historical context, the main purpose of depth stencil is to control whether anything gets written to the render targets. So it would make sense it would be the same logical stage where the right blend operations occur. So yeah, we figure out which pixels or what the pixel values are, and then whether we put them out to the frame buffer, it all happens in this last stage. Pixel shaders can do alpha testing and discard, which affect whether a write occurs. Um, and the earliest GPUs with depth buffers. Yeah, and that the hardware performed it at the end. Since yeah, that is a good point. You know, the depth buffer is a visibility algorithm implementation. It is a per pixel visibility test. And So not technically an optimization, but okay, it's a logical concept, construct, structure. Whether the GPU does it exactly like that doesn't matter as long as it produces the exact same results as the logical structure. Um, yeah, well, yeah. Uh, that's okay. So where does early Z fit in? Yeah, the logical pipeline is not everything. Early early Z exists and has been known about, and even specifications mention it explicitly because it's a thing that happens, so they might as well say it, even if because I think I'm pretty sure the Vulkan spec explicitly states this is where early Z would occur in the pipeline. Or if not, it has extensions that let you control it because it's something you want to be able to know about and make sure happens. Yeah, in the pipeline here, they can move depth testing above output merger and into the rasterization or between the rasterization and pixel shader storage because the rasterization stage produces the depth value that is put into the pixel stage, which could be obviously modified by the shader, but if the shader doesn't modify it, then it can be sneaky. Um, okay, so the driver will heuristically determine whether it's not heuristically, but based on shader and render states, uh, whether it's safe to do it early. So if we're doing opaque rendering, it's really simple. Calling the pixel shader is fine. Calling, since the only observable output is the render target rights, there's no visible difference between calling the render target right and calling the entire pixel shader before it even runs. Even if depth rights are enabled, early early Z operations can test the existing Z buffer first and then commit the Z if the test passes, while also allowing the pixel shader to run. Later on, if some other pixels or fragments ends up having a depth that also passes due to being closer, that's fine since the render target results will just get overwritten. Yeah, that's what I understand. Doesn't matter the order, you get the same result. Of course, just because the output is the same doesn't mean a different order is good. All orders are the same performance. We really do want front to back rendering if we're doing opaque geometry so that we're not wasting bandwidth writing to the depth to the output buffer and then overwriting it again and again and again. Overdraw is the term I know for that. You can do a depth only prepass. So you only create a depth buffer and then you read from that when you're doing the actual pixel shading. Yeah, hardware is pretty clever for figuring out it can do that while just keeping the pipeline working. Okay, here's the sample app. Let's draw two triangles front to back. The green is the front, the red's the back. There's 648,000 pixel shader invocations for these triangles. We reverse the draw order, we get 440,000 pixels, which is less. And that's because this one was back to front, and this is front to back, and we want front to back to get best performance. Okay. Early Z is still kind of a driver thingy, driver optimization. Granularity can vary depending on the hardware. Ooh. Earliest PC hardware did so with hierarchical depth buffers. Fun. Separate buffer with min and max depth values for region of the buffer. Allows for fast and coarse Z-call without requiring the bandwidth of reading the full depth buffer. Yes, hierarchical Z buffers are still a technique I see people talking about being a huge performance win by reducing bandwidth of unnecessary reads, or not unnecessary, but you create a hierarchical Z buffer, and then you can coarsely determine whole clusters, whole chunks, whole tiles, whether they will need to be tested or need to be executed or not. When does early Z not work? So opaque geometry is a good one, but not every case it allows it. If the shader discards or has an alpha test, yeah, I mean, if you're doing depth buffer writes and you discard after you've discarded, then that ain't gonna work. Yeah, discard is effectively dropping the pixel, but if you've already written out the Z buffer value, then you've written out the Z buffer value, but not the render target output. Yeah. Huh. Okay, so hardware still does some stuff to make it faster when early depth tests to do some early depth testing. Discard doesn't change the depth value. It merely makes the write conditional. Okay. So the rasterizer outputs all the stuff. We'll have a hierarchical Z cooling depth stencil test, and we won't have the early depth stencil test, and then we'll have the late depth stencil test. So when we split the depth stuff like that, we allow early Z cooling for discard scenarios. But that can have adverse effects on the early Z cooling rate. So looking back at this, we'll have the discard in the shader, which never runs, but we have 582,000 pixel shader invocations, which is not the 440,000 of the best case we had above. Um, A lot of the pixels from the further triangle are going to get accepted by the early Z test before the Z buffer has been updated by the closer triangle. Can try to verify whether that's happening by putting a global barrier between the draws. And with a barrier, yeah, we wouldn't want to do a barrier in practice. We only do it to confirm the findings. Okay, yeah, thanks for confirming that the Vulkan spec does explicitly mention early fragment tests. I think not mentioning it in the abstract pipeline is more of a historical artifact. I think D3D12 would want to, but um, it's still kind of abstract and weird to think about because it's not a explicit thing that happens, but this kind of conditional behavior. Okay. We can confirm that clearing the depth buffer to the closest possible value results in no pixel shader invocations. So it can be good practice to render non-alpha test opaque geometry first, or at least ones that have good occlusion chances. Only performing discarded at depth prepass followed by a full opaque pass with equal depth testing can also be effective. So the main thing is we want to avoid pixel shaders that are heavy from being run unnecessarily. Because if we're re-executing, or not re-executing, if we're executing pixel shader evaluation and throwing the results away, that's just wasted time. If we aren't writing depth values, early Z is compatible with shader discard. Well, that's good to know. Because depth buffer doesn't need to be updated in any case, so it's fine to do it early and call the shader. Yep. So in particles and transparent draws, without affecting early Z, it can be used with discard. Something to note, implications to early Z apply as long as your compiled shader instruction stream contains any discard at all. Right. The driver doesn't want to solve the halting problem and find out whether your shader actually discards if it's like in some conditional case or in a loop that has a condition or some silliness. It needs to decide that before compiling or as it's compiling your shader. It must decide that. It can't decide that as you're running the shader. That's a can of worms to think about. A runtime branch on a constant or uniform to avoid a discard can still, yeah, so you can't make early Z happen by putting your discard in a branch. Oh, so exporting coverage from Pixel Shader with SV coverage or GL sample mask has the same implications as performing a discard. So it's the same rules. Yeah, the depth value used for depth testing is gotten by interpolating from triangle vertices. Of course, if a shader overrides this value, then, well, it overrides it. So you can set that. So that's called depth export. Yeah, depth export would, in my mind, immediately make early Z go away and be completely gone. Yeah, hardware has no way to know without executing it. So it has to fall back to late Z. Oh, yeah. Even if you're not writing the value, it's the only way to get the right output from the pipeline. Oh, D3D11 added variants of depth export, collectively known as conservative depth export. These variants add a constant constraint on the depth value output by the pixel shader in the form of an inequality. SV depth greater equal. It lets you write a depth value with a constraint that it must be greater than or equal to the natural pixel depth that was calculated by interpolating it. Oh, okay. So it's saying the shader can only write a depth value greater than or equal to the one that was came in from the interpolator. It allows the hardware to safely enable a degree of early Z despite the final depth not being known until pixel shader executes. The inequality has to oppose the inequality used as part of the depth render state. So our SV depth greater equal, let's say we have depth writes disabled, but our depth testing enabled with less equal depth function. The driver and hardware can determine that a pixel shader can only increase the natural depth value from, yeah, it can only add to the interpolated value. So if the natural depth test fails, the pixel will always fail. So we can safely cull it with no discernible effect. Yeah, similar situation to shader discard. Yeah. Oh, yeah. If we combine depth writes with conservative depth export, it's more involved. So depth writes can't be committed before the pixel shader executes, since we don't know the final value. So we have to postpone the depth write until the late Z stage. We can still cull as it does the discard. It retains and it still has the advantage over arbitrary depth export, even when depth writes are enabled, with still some caveats about reducing culling rates that apply for discard. We have the example app with the full shader unification for both triangles. Oh, that's interesting. Okay, so UAVs, storage texture buffer, storage buffers. Okay, things are only getting more complicated. Pixel shaders will let us make arbitrary writes to textures or buffers, also cause the hardware to switch to late Z. So early Z works when the pixel shader is pure with no side effects, but if you're writing to a bunch of textures, then that no longer occurs. It's no longer a pure function that only writes to the render buffer. It also writes to a whole bunch of other stuff. So drivers have to go back to late Z. Unless early Z is forced on, which is a feature that is added to APIs. So, okay, yeah, it is totally a part of the pipeline now because it was added to the API. While UAVs ignore depth stencil or depth testing behavior makes sense through the lens of logical, it's not useful for a lot of things you can do with arbitrary pixel shader writes. The OIT algorithm, which appends transparent fragments to a linked list that can be sorted later. Appending fragments that are occluded by opaque surfaces makes no sense. And manually performing depth testing the shader doesn't save you the full cost of executing the shader. So in D3.11, okay, if it's added in D3.11, which definitely predates Vulkan, then that explains why Vulkan has it, because it is just describing what the hardware already has. Okay. Tag your pixel shaders with early depth stencil attribute. Exactly what it does exactly what it says. Forces all depth and stencil operations to happen before the shader executes, and then requires that the pixel shader be culled entirely if the test fails. Gives us what we want. We can cull the shader and then still perform our side effects. This is clearly great and useful, but before you do that, consider what it means to fully move all depth and reads and writes to before the pixel shader stage. Any kind of depth export is completely incompatible, and those shader depth outputs are completely ignored. It also breaks discard if the depth writes are enabled. The discard will prevent render target writes, but the depth buffer write will have already happened before the discard occurs, and thus a new depth value will still be written. Ugh. Discard without and discard with early depth stencil. Okay. Yeah, you wouldn't want the right half. The right half image are still applying alpha testing, but they're including each other as if there was no alpha testing. Okay. A simpler example shows what's happening more clearly. We can see the alpha transparent texture is fully occluding the background image, background triangle. I mean, if you're not using discard, early depth stencil is probably fine. Or, depth export UAV, writing to UAVs or anything else that's a side effect. Performing the depth test and write early is fine since there's no possibility for pixel shader to modify the depth. Okay. Okay, forced early Z with UAVs and depth writes. So let's get crazy. Use UAVs together with depth writes and forced early Z. What happens? You still get a race condition between overlapping pixels. Yeah. While the early Z depth test and update can cull an already occluded pixel before its shader has a chance to run. This will only happen if the triangle containing culled pixel was submitted after the triangle that occludes it. If they aren't in that order, then the closer and further pixels can run concurrently and will race. Oh, oh God. I didn't realize that race condition. I guess, I mean, it's baked into the pipeline that you're not doing atomic depth buffer writes anymore, where you're basically just going, oh, if this doesn't get cold, write it later. So that would be a race condition. Okay. Oh, there's more to just explore. There's rasterizer order views and / fragment shader interlock. Factors into the early Z depth write. ROVs guarantee two things: that pixel shaders mapping to the same coordinate will not have overlapping accesses to the ROV resource, can safely perform rewrite and modify operations without requiring atomic operations. Kind of like the ROV is the atomic resource. But accesses to ROV resources happen in API submission order, similar to render target write blending works. If you're not using depth writes, then the results you get from ROVs plus early depth stencil are straightforward. You only get writes from pixels that pass the depth test, and those writes will happen in submission order. Very handy for OIT, similar. But what about if the depth writes are enabled? You should again get results that match old school render target blend writes, where the last visible write from the closest pixel that ultimately passes the z-test is the one that wins. Getting these expected z-order results assumes that the early z happens in order of API submission, such that you get one of two results when two pixels overlap. The closer pixel performs z operations first, and so the further pixel thread is cold before it runs. The further pixel runs first, but the top pixel is guaranteed for its write to happen the second and thus be visible because the ROV rules. If we think about it, this is this really is the same as if we have just used regular render target rights instead of ROVs. The rights happen in the submission order, and so the ZOPs must also happen in submission order. It does seem like that works, but like anything in the article, try to verify it yourself. This approach would still be incompatible with discard or depth export, just like any other pixel shader that forces early Z. There's an inherent performance overhead of ROVs, very dependent on the hardware and amount of parallelism, overdraw, and blah, blah, blah. So here is the chart. Whether our depth rights are enabled, yes, no. Whether which shader features, depth export, conservative, UAV, and then adding in if you're using a early depth stencil attribute. Oh, wait. Why is this? Is this not? Is this table longer? Oh, ROV rights is added. Okay. Okay. So this is, yeah, all about when early Z happens and if it happens and what to expect. Okay. Yeah, okay. There's stencil stuff also happens and can get early Z optimizations, but this article doesn't discuss it. So good to know. Cool. Anyone have comments about the article? Questions or discussion of any sort?
Still haven't decided if I want to do forward or deferred rendering,
I mean,
even after reading this.
I can tell you if you want to do what the cool kids are doing, you just say, screw either of those. Let's do visibility buffer rendering. Where was it mention it? I had it flashed into my head when it talked about, oh, well, what if you use a depth prepass where you render all of your depth values, and then create a depth buffer, and then the next you re-render everything again with the depth buffer already seeded, so you get a very quick, pass fail instead of having to do the storing and incrementally building up the Z buffer. It's like, well, that requires rerunning all of your geometry a second time, and the visibility kind of falls out of, well, what if we do a Z prepass but then just ingest the depth buffer and render everything from that. And the way you achieve that is by having a depth buffer and a what's called visibility buffer, which is each pixel stores an index into an array, to summarize it really crumbly. And every index in that array is a different material. So you basically have a depth buffer and a material buffer, and then your second pass is taking the depth buffer and material buffer and then actually performing the operation to figure out the pixel value. It's like gbuffer on steroids. But there are a lot of things to that I cannot really describe in enough detail to say you should just do it because it's easy and fun. It's like, no, it's way more work, but it certainly has the attributes of being more performant in the cases that a visibility buffer can be more performant. Because it doesn't like things like transparency and pixel shader dependent value, depth values are not well handled by them. That makes sense.
Well, like one thing I was thinking about is like Like I'm thinking of messing with like standalone VR, which is like a mobile device.
Oh, yeah,
So deferred would have like a huge G buffer because there's
yeah,
you would have like two deferred, or you would
pretty
have two
much.
G buffers basically, and they're huge, they're massive resolutions. But at the same time, if you do forward, even if you do like the depth pre-pass, you still have like all these quads like from the triangles. Like I forget exactly what it's called, but you know when like,
Tiles?
well yeah, you have tiled rendering, but you know when when like how GPUs render things in like 4 pixels at a time,
Yeah, or
and if
4 by 4 pixels, 16 groups of 16. Oh, there,
yeah,
those,
so
oh, those are different quad than what I'm thinking of. Um, what are those? Actually, that was mentioned in the article. Quad
it's called quad
overshading.
overdraw
Yeah,
or something, right?
yeah. When you have a bunch of single pixel triangles, they need to compute to run all 4 lanes in order to compute the derivatives used for texture sampling and the depth buffer stuff. It's just it becomes a problem.
I think it's less of a problem for deferred, but it's a problem for forward because you're
Yeah,
constantly like redrawing. Like
yeah.
even though you have a depth pass to like filter out, like you have the depth
Mhm.
pre-pass, so you don't like have the pixel shader run multiple times. It only runs like once for the pixel. The thing
Yeah.
is that when it's doing the vertex shader is still drawing the triangle to do the depth pre-pass, so that's where you get burned by quad overdraw on or whatever it's called on forward rendering.
Hmm. Well,
At least as
I don't
far as
really
I
have.
understand.
Yeah, I am no expert. If this was a if I was on a Windows machine, I would consider pulling this project down and running it. But I am on Linux and I do not want to try to run a Visual Studio solution on Linux in a live setting. So I'm just not going to do that. So I think we can end the recording here.